Okay, let's get going. Today and next week, we're going to be talking about hierarchical models. This week we'll do some more of the introductory stuff, building on what was talked about in the Bayes rules reading. Next week we'll get into a little bit more advanced treatment of these hierarchical models based on the reading from McElreath. But if you've understood what we've been doing thus far, it's not as if hierarchical models are that much of an additional stretch. But if you sort of take the perspective of, from where you were at the start of the semester, or take the perspective of someone who hasn't taken a Bayesian class, then hierarchical models are seen as like a very advanced regression sort of technique, whereas, from a Bayesian perspective, they're just kind of research. Like almost all Bayesian models are hierarchical in some respects, and that's just taking advantage of what the Bayesian framework gives you, and taking advantage of what algorithms in like STAN give you, which is draws from the joint posterior distribution of all the unknowns given the known data that you have, inclusive of any structure that data might have. So, like every other week, since this involves STAN in a significant capacity, need to be aware Columbia University's policies regarding conflict of interest. So what are hierarchical models? Question mark. So from a Bayesian perspective, which is the perspective we want to be looking at things from, a hierarchical model is nothing but a model where the prior for one parameter is conditional on some other parameter. And just to kind of emphasize that this is not too big of a leap from what we've been doing before, we've already seen several examples, at least with hierarchical data. So bowling example, all the way back, week 2. Or, and 3, and 4, and 5, whatever it was. The probability distribution for x2 depends on n, and n is 10 minus x1. So the distribution for x2 depends on x1, and if the frame hasn't happened yet, then x1 is a random variable. Obviously, both of those are dependent on what we call theta, the inability of the bowler. So you get like x1 given theta, and then x2 given 10 minus x1 and theta. That would be considered hierarchical data. Now we're just going to do it with hierarchical parameters in a hierarchical model. Also had a similar thing on homework 3 when considering how many vetoes get overridden in a congressional term. Well, that's, binomial given the number of trials. And the number of trials is the number of regular vetoes. And on homework 3 we had a negative binomial, or whatever it was, model for the number of regular vetoes. And then there's a layer on top of that, how many of those regular vetoes get overridden. I think at some point we did bivariate normal. Can't remember exactly when that was. But yeah, probably when we were talking about HMC or something. you can express the bivariate normal distribution as marginal normal distribution for the first thing and conditional normal for the second thing given the first thing. And conditioning on the first thing shifts the mean and it scales down the standard deviation. So that is another example of hierarchical structure, but that's really just using the multiplication rule, the joint distribution of some collection of variables is or can be written as marginal distribution of some subset of those variables times conditional distribution given the complement set. But even when we were doing linear models, we do things with the generative model, like sigma is drawn from an exponential distribution with rate 1 over r, or that should be just r, expectation 1 over r. Then the errors are, each of them are realized independent from a normal distribution given the realization of sigma. So this sets up a joint distribution between sigma and all the errors that we, draw from in a one-step, two-step procedure. And that's all we're going to be doing today with this stuff, hierarchical models. So it's just another application of the rules of probability, specifically the multiplication rule. Since we're going to be talking about it in terms of parameters, that's conceptually going to involve an integral, but as we've seen by now, we've gotten all this time, never done a single integral. By hand, we're going to be doing that from drawing from the distribution of the variable that we have marginal, and then using the realizations of that to draw from the distribution that's conditional on that. Conceptually, we can integrate over whatever we want to. And if we don't care about these, then we don't have to worry about them. If we only care about that, then that's fine too. So we can choose what we care about. But in order to draw from the right posterior distribution, we have to draw from the joint distribution of everything. Unless we can integrate something out analytically. But if not, we just draw from everything. And then use, the parameters that are important to us. And so, from a non-Bayesian perspective, hierarchical models are a bit different. From a non-Bayesian perspective, everything Bayesian is a bit different. But from a non-Bayesian perspective, hierarchical models are different from not hierarchical models in some fundamental ways. Whereas from a Bayesian perspective, it is really just like an evolution of what we've already been doing rather than something that's fundamentally different. The framework for Bayesian inference was always general and rich and extensive enough to incorporate this stuff. We just didn't really get to it until now. So inclusive of that are modeling technique known as splines that gets back into what we were talking about with the previous homework and that article by Leo Bremen, talking about the differences between data modeling culture and algorithmical modeling culture. And, linear models, that's something that Bremen would have associated with data modeling culture, very popular still today, but particularly back when the article was written. And those are linear functions of the coefficients. So when we say something is linear, it means linear with respect to the betas and gamma or alpha, whatever it is. No gamma squared appearing in a linear model. Now, oftentimes, such models are also linear with respect to the predictors, or generalized linear, if we're applying it. inverse link function or something like that. But you're always allowed to include nonlinear functions and predictors, and we have done so at various points in time. So we have an interaction term between like number of seats held by the president's party in the House and the number of seats held by president's party in the Senate, something like that. That's gonna, two variables in the data frame being mapped to 3 columns of the X matrix. So you've got House margin, Senate margin, and product of those 2 margins. 3 columns of X, and when you make more columns of X from fewer variables in the original data frame, then there's going to be a nonlinear relationship with respect to the variables in the data frame. But that's still part of a linear model because it's linear with respect to the betas. Can also have, it's not a great idea, but you can also have polynomials. So one variable, such as age, in the data frame, generating k columns in the X matrix, with one variable such as age, raised to the power 1, and then another column, age raised to the power 2, age squared. Could have another column, age raised to the power 3, etc. Now, this is not a great idea, not only because if you do it with too few data points and too many powers of the predictor, you can overfit the data that you have, even if you have some proper priors on these things. So if you're going to do that, you really need rather strong priors. But raw polynomials are not a good idea anyway. Anything on a computer, it doesn't even have to be Bayesian. Like, you should really never be using a raw polynomial. But conceptually and mathematically, they're appearing a lot of times. Also saw nonlinear relationships. You have one factor variable. So the things that we did last time, or in recitation, where we had modeling support for stem cell research as a function of someone's religious beliefs, and had sort of fundamentalist, moderate, liberal, etc. So if you have a dummy variable with k plus 1 levels, that's going to generate k dummy variables in X, leaving out the baseline. And then, obviously it's going to be like a nonlinear relationship, even though we're just multiplying by dummy variables, with respect to the original variables. So this nonlinear function of predictors happens whenever you put a nonlinear function of a predictor into X, inclusive of functions where you start with like one predictor and you make more than one column of X with it. And that's what happens with splines, which are a much better way than polynomials to allow some predictor to have some nonlinear relationship to mu, even in a linear model. But also it can be done in a GLM where it's a nonlinear relationship to eta. This is considered preferable for a number of reasons, but with a polynomial, okay, it's like relaxing the assumption that it's linear with respect to age, but assuming it's now quadratic. Now, quadratic includes linear as a special case, so in a manner of speaking, it's a generalization, but you're still making a pretty particular functional form assumption. Whereas there's other ways of doing it, splines inclusive, that make even weaker assumptions about the nature of the relationship between the underlying thing, let's say age, and the outcome. It's sort of, with splines, Gaussian processes, which we'll talk about in a second, the relationship can be pretty much any smooth function. So let's look at one of those. Again, going back to the data on the midterm. which was on the French municipalities, and the goal of the research was to ascertain what's the causal effect of a municipality getting just enough population to cross the threshold where they need to change their system to use proportional representation at the municipal level rather than a plurality system, which is required by law for municipalities with like less than 3,000 people or whatever it is. And so both RSAN-ARM and BRMS utilize the MGCV function, which has this additional syntax that you can put into formulas with the S function, which stands for smooth. So this is saying turnout in 2008 is going to depend on whether the municipality had a PR or a plurality system, and it's going to be some smooth function of the logarithm of the ratio of the population to the threshold. So this relaxes the assumption that was made in the original paper that turnout is linearly related to logarithm of population. And that assumption turned out to be like not bad, but there was no real reason why you would want to make that assumption at the beginning. There's nothing about the theory in comparative politics or whatever it may be that says, oh, the relationship between turnout and population is linear except for this like one bump that happens right when you cross over the threshold at 3,000. And if you think about it, you would be hard pressed to think of any theory in the social sciences that goes like this. You know, there's a linear relationship between some outcome and some predictor, and if the relationship is anything other than linear, then the theory is wrong. That's not the way any theories are developed in the social sciences. The most common thing that you see is, okay, here's a theory. There's a positive relationship between this and that. Or there's a negative relationship between this and that. That's usually what the theory says. But when people go to test those theories, they almost invariably assume or make a stronger assumption that the relationship is linear, or generalized linear, or quadratic, or something like that. But you could have a positive relationship that's like this, or like that, and maybe flattens off, but still gets going positive. You can even have a relationship that's like this, and then maybe comes down a little bit in the end, like for really old people or something like that. And if you estimate it, as somebody said, oh, there's a positive relationship between this and that. And then, you estimated a thing, and it was like mostly positive, but then it kind of plateaued and then decreased a little bit at the end. And if you said to the person who came up with the theory, look, it's not a positive relationship across the entire range, the person who originated the theory wouldn't be like, oh, I guess my theory is wrong. They'd be like, no, my theory is right for almost all the range. And then, it's like decreasing maybe a little bit for, very extreme ages or something like that. And so when people say there's a positive relationship between this and that in theory, they don't even mean like strictly positive over the entire range of like all conceivable values of the predictor. They just mean like over the range where most of the data are. So that's usually what happens, and very almost never is a sort of necessary condition for the theory to be that the relationship to the predictor is linear. Maybe a little bit in the theory of exchange rate movements. So, if something happens in the United States, should be a linear relationship to the euro, because like currencies are exchanged in, or floating currencies are exchanged with some multiple. But that's about the only situation I can think of where if there was like, a nonlinear relationship between the amount of euros you could buy and the number of dollars you handed over, that would like destroy the theory of exchange rates. But anyway, that's not even what we're talking about here, or any time else really in social sciences. And so we have like a theory relating to one variable that PR systems encourage more turnout, and not even any particularly strong theory, maybe none at all, about the other predictors that may go into this model, such as population, but we need to be conditioning on population in order for this regression discontinuity thing to make sense, because whether you have a PR system or a plurality rule system in France depends on your size of the population of the municipality. And so you could call the GAM function with one of these S businesses to specify this should be some smooth but possibly nonlinear function. And I call it with fit equal false because I just want to look at the X rather than actually fit using the MGCV package, which is not using MCMC for the most part. It actually has the option to do some stuff in JAGs. But anyway, the maintainer of this package, which it comes with R, it has a long history, says a lot of Bayesian things, but when they go to estimate stuff, they just do it with optimization. Actually, penalized stuff, but not really a Bayesian estimator. So anyway, when you look at this X matrix, it has 10 columns, even though I only gave it 2 things. So what are all those extra columns doing? How do they get there? What effect do they have? Well, we can come up with a generative model for the situation where we have one or more predictor variables in the form of a spline. We can do this with generalized linear models, but let's just do it with linear models today. So continuous outcome, as we've done before, defining the observed outcome as the sum of a conditional expectation for the observation and some error. And that error is distributed normal with standard deviation sigma of epsilon. And it looks like I made this mistake repeatedly today. With the standard deviations have this exponential prior with rate r over epsilon and expectation reciprocal of r. That's was intended to be how we've done things all semester. And then mu is going to be some intercept. This is one situation where you might want to do it relative to centered, uncentered predictors, because log ratio is already made so that 0 is the threshold between proportional representation system and plurality rule system. So we have intercept treatment effect on the RU proportional representation system plus the sum over K of beta times all these other x's that are not the PR variable. And so we have a usual normal prior on the intercept, the usual normal prior on the average treatment effect. But what's different about these is our prior for the betas on the population business is normal. Okay, that's normal. Expectation 0. Okay, that's normal. But with standard deviation sigma of beta, where sigma of beta is unknown, that we also have a prior on, which can be exponential. And the way to think about this is, okay, and we're going to estimate or draw from all of these, but if sigma is small, then the prior on beta is going to be very concentrated around 0. So multiplying whatever it's multiplying by some number that's very close to 0. And close to 0 times anything is close to 0. Well, close to 0 times anything fixed is close to 0. But x is fixed. Anyway, so now our prior on the betas depends on the unknown. Whereas what we've been doing for the most part up to this point in the semester is saying, okay, the prior expectation and the prior standard deviation on these betas are fixed. Now we're saying, okay, one or more of those can be unknown, involving a parameter that we also have a prior over, and now we're going to draw from the distribution of everything. So questions about that other than why did I put the reciprocal instead of just R? But these are different standard deviations, and so these can be different priors. This is the standard deviation of the epsilons. This is the standard deviation of the betas across the 9 columns that I have here that were created from my one thing in my data frame, log ratio. So in terms of what would the code look like to draw parameters, so we have a usual prior on the intercept, based on the previous year's or elections turnout, you might say it's around 70. Could have some prior uncertainty about that. We have prior on delta, which is just a regular prior, so you might say, okay, I think you might have a small positive effect to have a PR system rather than a plurality rule system for a variety of theoretical reasons that have been talked about. And so here I managed to do the R's correctly. So prior R for sigma epsilon 0.1, so expectation of 10. Whereas for beta, R of 2, so expectation of a half. Is basically saying I don't think the betas differ too far from 0. And as we'll see in the context of the spline, how far these betas differ from 0 affects how nonlinear the relationship between the outcome and log population is. And so if it's really concentrated towards 0, it's pretty much a straight line. If sigma is large and the betas differ from 0 a lot, you can get a very nonlinear function. And so sigma governs the wiggliness, which is the technical term in the literature, of the function that we're estimating between turnout and log population. So, okay, I've got my prior hyperparameters ready to draw, intercept, coefficient on the PR thing, draw my sigma of the betas, draw my sigma of the epsilons, and then beta is going to be R by 9 matrix. Mean 0, standard deviation, realizations of sigma beta. And so then drawing the outcomes from these draws, not too complicated, particularly if you're sort of familiar with matrix times vector things, so where you can do all this at once instead of sort of explicitly having a summation. Now, to bring it back to the Bremen thing, splines, or more generally estimating nonlinear functions, is today associated with supervised learning, or what Bremen was calling back in 2001 or whatever, algorithmical modeling culture. But Historically, that's not super accurate. Certainly Bayesians were talking about these ideas even back before 1990. But they were sort of talking about it and they're like, oh, wouldn't it be nice if we could estimate this model? Like we can draw from this model pretty easily, just like this. Well, they didn't have R before 1990, but you know, the languages that they did have, they could draw this. But they're like, we can't really update our beliefs about the parameters because we don't have an algorithm for doing Bayesian inference when we can't do the denominator analytically. And so although Bayesian people were talking about it in like the 1970s and stuff like that, and a lot of the work on this sort of stuff was done by someone named Grace Waba, who was at the time, I would say, kind of proto-Bayesian. But you know, everyone at the time, not everyone, but the people who were thinking about these things at the time were all sort of proto-Bayesians. They just didn't have MCMC. And so the only real reason why this hadn't been widely done when Bryman wrote his article was that it hadn't been very long that anybody had an algorithm where you could do this in a fully Bayesian way. Yeah, that started to change in 1990, but the algorithms were still kind of primitive. Arguably, it wasn't until Stan got started. Well, it got started in 2011, but the first release wasn't until the next year after that we really had algorithms powerful enough to where you could do the posterior distribution of a model like this rather easily. And you can do it both with BRMS and with RStanArm. So to do it with RStanArm, you call the stan_gam4 function, which is intended to, or was originally intended to emulate the gam with two m's for function in the gam with two m's for package. That's also maintained by the same person who does the MGCD package. So you can put the S business into the formula that goes into stan_gam4, so your data. Here I just do one chain in order to not have it take up so much RAM. And we have a prior on the intercept, we have a prior on the coefficient on the PR thing, and we have a prior on exponential prior on sigma that goes into the errors. And so this takes longer to run, but still it works really well in Stan most of the time. And you can see the output. So at the top here we have posterior median on the intercept 75.5, totally reasonable. Posterior median on the coefficient for the PR dummy variable 0.7 has a posterior standard deviation of 0.2. So we're quite sure this indeed has a positive effect. But then we have 9 other variables that have coefficients, rather small coefficients for the most part, but they're like 9 columns of X that were derived from one predictor in the data frame, namely log ratio. And it's like, what do I do with those? Well, one option is to do nothing. Like the PR business, the coefficient on PR answers the question that you set out to answer. Is there a positive relationship? So yeah, so in a manner of speaking, we're done. But it also estimates what it calls smoothing terms. And in Greek, that's the standard deviation. Go away. The sigma betas. There's actually 2 of them in this model. Like I was saying before, the larger those are, the more nonlinear the relationship is. The smaller those are, the smaller the betas are, the more linear relationship it is. And the sigmas govern how far the betas differ from zero. And so if you look at the posterior distribution, well, one of those seems like not so big, but the other one is actually pretty big. But this actually turns out to have less effect and it's less precisely estimated. So if you don't need to worry about any of these things, then you can just say, okay, there are variables I'm conditioning on in order to get a better estimate of the thing that I care about. But if you do care about the relationship between the logarithm of the population ratio and the outcome, then we can definitely ascertain that. It's just in this model, like every model that has any amount of nonlinearity to it, we can't interpret any of these things in isolation from each other. We have to interpret their collective influence on the function relating logarithm of population ratio to turnout. And like everything relating to posterior distribution, that is best depicted with pictures rather than a table of numbers on coefficients that don't really have any interpretation in isolation from all the other ones. But we can look at this plot, which is conveniently produced by plot underscore nonlinear in the RStanR package when you estimate one of these spline things in stan GAM4. And so this, sort of irrespective of whether you're PR or plurality rule system, this is depicting the smooth function that we estimated between turnout in 2008 and the logarithm of the population ratio. And lo and behold, it turns out to basically be a line. That's not something we assumed, well, it was something on homework 2 or whatever, or the midterm. On the midterm, we assumed it's a line, which is actually it was in line with what the original paper did. It's what almost everything you see in social science does. But we didn't have to, and arguably we shouldn't, have assumed that there was a linear relationship between population and turnout from the outset. Rather, it would be better to make weaker assumptions, and if it turns out to be basically a line, then, cool. But if it had turned out to be something that's not a line, well, that would also be cool as long as it's like smooth. We could have estimated what that function was. Moreover, we get uncertainty intervals around this curve. Fairly narrow ones because we conditioned on a lot of data. But we get uncertainty intervals as well. And so, in other situations, maybe where we have less data, the uncertainty intervals are wider at some points along there, and you may say, okay, this could be a line, or it could be something that's like increasing at a decreasing rate, like very slowly or something like that. And so your uncertainty intervals may encompass a variety of functions, and that's fine too, because your posterior inference on whatever it is you're inferencing about can marginalize over all the functions that this could be. And thereby propagating your uncertainty about functional forms to the conclusions that you're drawing from this model, such as the effect of PR or trying to make predictions or things like that. And so that's one way of allowing fairly arbitrary nonlinearity with respect to a predictor into a model that we can estimate just as easily as any other model, pretty much, using Stan. And that's pretty cool. In other situations, A lot of situations. Maybe where you have less data. It'd be reasonable to assume there's a nonlinear function, potentially nonlinear function. But imposing the restriction that the function becomes linear as it goes past its extremes. So linear through the most extreme data points that you have in the data set, and then just keeps going linear beyond that. So if this were age or whatever, to say, okay, the effect of whatever it is, it can be nonlinear in like all the intermediate ages. But if the oldest person you have in the data set is like 94, then say, okay, like whatever the slope is for the 94-year-old, just keep going for everyone who's older than that, linear. And those sorts of assumptions are often good to make, even if you don't necessarily have a great reason why they are. Because if you restrict the nonlinear, well, let me say it the other way around. If you allow the nonlinear function to be like anything going out to infinity in both directions, then you can get some really crazy stuff that just doesn't make sense. Like, not just for old people and young people, but for everybody. You can get a really crazy function. Because it sort of tries to do too well at the extremes and isn't trying hard enough to do well in the middle where most of your data are. And so if you put some sort of restriction on the edges of the nonlinear function, then you often get a more reasonable model throughout. And so one of the ways in which you can restrict nonlinear functions is to say, okay, they're linear through the extremes, but they can be cubic or piecewise cubic in the interior of whatever variable, age or population or whatever. And so these polynomial splines are constructed in such a way, this one's cubic, that's probably the most common thing, is to say, okay, between like here and there, it's a cubic function. But it joins with another cubic function in its next window over at the same point in such a way that the derivative coming this way is the same as the derivative going the other way. And so it looks to the eye like it's a smooth function. And it actually is a smooth function in that it's going to have two, in the case of cubic, it's actually going to match the first two derivatives. So it totally looks like a very smooth function. It actually is like twice differentiable. But anyway, it allows you to be sort of piecewise polynomial in the interior, but then it makes the restriction, okay, once you get past the edges of your data, then we'll restrict the derivatives to be linear going away in both directions from the edge. And that can be accomplished by restricting the derivatives to this piecewise cubic function business. And so that construct is provided in the RMS package. So the package is called RMS for regression model strategies. So BRMS is actually picking up on the RMS name for Bayesian regression modeling. It's a standard whatever. But anyway, the guy Frank, who came up with the regression modeling strategies package and also book, is very much Bayesian. But when he first started writing the book, Stan wasn't available, and so the tools for doing Bayesian stuff were not as readily available as he would have liked. But now he's, I think, trying to do everything he can. And with Bayesian stuff, even though he's operating in like public health, where there's like anything else, there's not a lot of Bayesian stuff out there. Anyway, in the RMS package for regression modeling strategies, there is the RCS function for restricted cubic spline, which will take the variable that you give it and make the appropriate number of columns in X so that it has this piecewise cubic in the middle and linear going to the edges. Structure to the function, and then it just needs to estimate some coefficients on the corresponding columns of the X matrix. And so that can be done with stan LM, and that's maybe not a bad way to do it, because stan LM allows you to put a prior on the R squared, like what you think the most likely value of the R squared is. In models like this, or other splines, other sorts of nonlinear things where we can't really even interpret one parameter in isolation from the others, it's hard to specify marginal priors on those things. It's easy to do, but it doesn't really make sense. So in a situation like that, it's even more attractive possibility to put a joint prior on things. And this prior on the R squared sort of pertains to the coefficients collectively. We talked about this a little bit, but this is the prior on the coefficients that has maximum entropy given an expected log R squared. And so here we're saying, okay, maybe we can explain a quarter of the variation in turnout with the PR thing and the population thing. And then, we do that, have a usual prior on the intercept. Don't need a prior on the sigma because that's linked to the R squared. Anyway, then we get estimates, or point estimates, but these are, again, just one number out of the 4,000 that you get back. Maybe a little bit of a larger effect, maybe a little bit more uncertain. And then you have these other things which pertain to the first, second, and third derivative of the function that got estimated relating turnout to log ratio. And if you can say, well, I don't really care about that function, and I certainly don't really care about the third derivative of that function. Okay, if you just sort of think that the first, second, and third derivatives are small, then the level of the function is what you're looking at, and so it seemed to suggest a negative relationship between population and turnout, consistent with what we saw here. And so the fact that these are not so different from zero, particularly compared to their posterior standard deviation, means you basically found a line. And some people would look at this and say, well, if it actually is linear, you should just assume it's linear. That would make it easier. But we don't totally know that this is exactly a line. It seems to curve a little bit. We have some uncertainty, particularly in the bigger municipalities, etc. And so by treating it as nonlinear, even if you estimate something that's basically a line, you allow your uncertainty about it being basically a line but not totally a line be pushed through to your uncertainty about what is the effect of having a PR system, which is what you really want to be getting at. And so what we did on the midterm, we got an estimate that was maybe similar to that on the PR thing. But that estimate is given that the relationship is a line. The estimate is whatever we found it to be on the midterm. But there's no real reason to say given that the relationship to population is a line. And so we can weaken that considerably to say something like that, okay, given that the relationship to population is smooth, here's the estimate of the effect of PR. And smooth in this case turns out to be basically a line, but not totally a line. And in general, I think you should be, with your continuous numerical variables, or even something like age, which is like integer, from a Bayesian perspective, you really should be using some sort of nonlinear form on those, because you're rarely, if ever, in a position in the social sciences to where you could be so sure that the relationship between the concepts is linear, that you're not willing to even entertain anything else, despite the fact that everything you see in the literature is going to assume linear relationship to the predictors, pretty much, maybe an interaction term here and there. So yeah, the literature is willing to make excessively strong assumptions, but you definitely don't have to, and you shouldn't, because the linearity business is not a necessary condition for whatever theory you're talking about. It was something that was necessary for estimation in like the 1960s. And like a lot of other things from the 1960s just never changed, even as it became possible to do. Now, I should point out, there are frequentist versions of models that have these smooth functions, like in MGCV and whatnot, where they're going to use penalization, and that's what supervised learning does, to change the mode. But you're still going to get sort of a point estimate of the function, rather than saying, okay, marginalizing over what the function could be. Here's my predictors and whatnot. But if you did this without penalization, and even if you do have some penalization scheme, it's an awful estimator from a frequentist perspective. And it's awful from a supervised learning perspective because it overfits the data that you have. Because you created 9 predictors, or 9 columns of X out of 1 predictor log ratio. And then if you did this with maximum likelihood, found the coefficients such that the most likely data set to observe is the data set that was observed. And so the fit at the most optimistic point in the parameter space is going to be worse if you applied those parameters to any other data set that could have been constructed. And so, in part for that reason, you don't see the frequentist version of this done very much. So it's not a good estimator, and also maybe more to the point, like, how do you test the null hypothesis that that's not, or how do you test the null hypothesis that that's 0 if it's not a line? Like, it's downward sloping throughout. It turns out, but in other situations, it could be like positive up here and then like that. And so then it would be like a little bit positive and then a little bit negative. And in a situation like that, well, how do you test the null hypothesis that it is 0? Like, it never is 0, but sometimes it's a little bit positive, sometimes it's a little bit negative. Maybe it's never very far from 0, all sorts of things. So that's probably the real reason why you don't see it done very much, is it does not lend itself to hypothesis testing. But it's an awful estimator from a frequentist perspective, like across random samples. From supervised learning, you really need to penalize it in order to mitigate the overfitting problem and obtain better predictions in testing data. That's one of the things that Leo Breiman railed about. But even better than all that, which is to say much better than all that, is marginalize over the possible functions. Analyze the fit averaged over what all the parameters could be, rather than only at the 1 parameters that were optimal with respect to the function, which is to say average fit is always worse than best fit. But average fit is what's most applicable if you think about predicting future data with one of these functions. So taking this a step farther, Gaussian process is, from a Bayesian perspective, weird name for a relatively simple concept which is a prior over smooth functions. So if you consider the distribution of all possible smooth functions, we can have a probability distribution over that. And like I was saying at the beginning, this is not really too much of a stretch from a Bayesian perspective, because we put priors on lots of different stuff, treating our beliefs about them as random variables. And random variables are functions. And functions of random variables are random variables. So what's really the big deal conceptually about expressing our beliefs about an unknown function among the class of smooth functions that might be, reasonable enough for a particular data set that we have. Now, so Gaussian processes are great, but unfortunately they require n-cubed floating point operations to evaluate the log likelihood function even once, where capital N is the number of observations that you have in the data set. So if you have 1,000 observations, you're looking at something that could easily take several hours to run, because Stan has to evaluate the log likelihood function millions of times. And each time it takes 1,000 cubed multiplications and additions and subtractions in order to evaluate the log likelihood function. So that's like 1 trillion. So yeah, like 1 million trillion floating point operations to get draws on the post-distribution. So this can be prohibitive from some data sets that you'll encounter in the social sciences. But if you have, 100, 250 or whatever, then n cubed is not that big a deal. So you can do these. And the BRMS package includes both a genuine Gaussian process thing and an approximation of the Gaussian process that is faster and not having n cubed complexity. And you can do that with just putting the GP business into the formula, and then there's some other arguments that you can put in if you're using the approximation that you can read about in the documentation, which has a link, I hope, to a paper of Paul that he co-authored with Aki and some other people in Finland about these approximations. And so you can estimate these nonlinear functions with almost no assumption except that you're considering the class of smooth functions, and you have a prior over that space of functions. That prior is going to have some additional parameters that also get estimated, and so you're going to have priors on those two. Those are just numbers that affect the nonlinearity and all that. So it's another hierarchical structure that can be used to estimate these things. And with this and some of the things that are a little bit easier but maybe have more restrictions on them, like restricted cubic splines or the splines in MGCB that we started with, I think emphasize an important thing to take away when reading Bryman's paper or papers like it that have followed, that when Bryman was basically mocking data modeling culture, but his arguments essentially mostly pertain to frequentists who dominated every culture and subculture within statistics for a long period of time. He barely mentions Bayesian stuff in the paper, but particularly with the benefit of hindsight. It might not have been so apparent at the time, particularly to someone like Raymond who isn't Bayesian, that the Bayesian framework from the beginning always was wide and encompassing enough to do both data modeling stuff and algorithmical modeling stuff, where prediction is the goal as opposed to testing of a hypothesis. What the Bayesian thing lacked was an algorithm to actually accomplish what the framework was, constructed to be. And so nowadays, particularly with the Hamiltonian second generation MCMC algorithms, we can do a lot of the stuff that within the Bayesian framework, we can do a lot of the stuff that Bremen was attributing to the algorithmical modeling culture. The splines, neural networks, we're not going to really talk about that, but we could. Random forests, those sorts of things, which are associated with supervised learning, are not incompatible with the Bayesian way of thinking about it. And we just lacked the algorithm to do it. So we had algorithmic modeling culture was already built into the Bayesian thing. We just didn't have the algorithm until past 10, 20, 30 years. Bryman, like a lot of people, didn't see that because the algorithm was just sort of barely getting started when he wrote that paper. But unfortunately, even after the algorithms became more sophisticated, the proponents of these supervised learning techniques went off in a decidedly non-Bayesian direction, where they obtained point estimates of this stuff and then, pretend that the past data in the testing set is future data to evaluate these things instead of doing what we do, which is to take the expectation of the actual future data that hasn't happened yet when estimating the ELPD and whatnot. And so, in part due to people like Bremen, the supervised learning or the algorithmic modeling culture has really grown from it was a tiny thing in 2001 to a huge thing today, and is completely dominant in tech companies and stuff like that. But Bayesian was also a tiny thing in 2000, but it hasn't taken off in nearly the same way, particularly not in the social sciences for lots of reasons that we talked about. Even though it was probably a mistake to think of what Bayesians are doing as being part of data modeling culture, even though there is modeling of data. But I think if Bryman had been more familiar with the framework and the history, he could have probably said more constructive things about the Bayesian approach that was, starting to get developed behind the first generation MCMC algorithms. But I think the big clue, which should have tipped Bayman off before he, started ranting about essentially frequentists, is that Bayesians had been ranting about frequentists for 75 years before Bayman wrote that article. So you might think, okay, well, whoever these Bayesians are think of themselves as doing something very different from what he sort of painted with a broad brush with these data modeling things, when actually, you can do pretty much anything you want with Bayesian output. Anyway. So all that being said, all this nonlinear stuff, there's a particular type of hierarchical modeling from a Bayesian perspective. Unfortunately, the introductory discussions of hierarchical modeling from a Bayesian perspective, such as that in Bayes' rules, sort of take as their starting point the thing closest to frequentist hierarchical modeling, rather than, I guess, coming at this from a more general Bayesian thing. And with frequentist hierarchical modeling, it depends, or it should depend, people in practice ignore this distinction, but should mathematically, philosophically depend on how the data were collected. In particular, are we talking about cluster random sampling or stratified random sampling? So what's the difference between those? With cluster random sampling, you proceed in 2 stages. First, you sample J large units from the population. So the most classical example of this is in education research, where the J large units would be schools. So maybe you sample from J equal 100 schools from the population of high schools in the United States, or something like that. And then within each of those capital J schools, you sample N sub J small units, which would be like students or classrooms or something like that, from within the little j school. And you do that for all the schools. So you might randomly sample 100 high schools, and then within each high school you might randomly sample 10 students. And so in the end you get a data set with 1,000 rows. But you have like 2 kinds of units. You have schools, the big units, and students within schools that are the small units. But you randomize the collection of both the schools and the students within schools. And moreover, there are certainly high schools in the population that you didn't include in your data, as well as students from each school that you didn't include in the data. But because you had a limited budget or whatever, you were just taking a relatively small sample of each, and then you did so randomly in order to make things uncorrelated and stuff like that. And so that happens sometimes. It happens a lot in education research. But it differs from what's more common in political science, economics, other things, and social sciences, which is stratified random sampling, which is fundamentally different in that you divide the population of the big units into J mutually exclusive and exhaustive groups, and those groups are not random variables. So most common situation with social science, political science, economics, things like that, would be to divide the United States into 50 or 51 states, if you count DC or something as its own geographical unit. So, California is not a random variable. It's fixed. It's not changing. At least its borders aren't. And moreover, when you do stratified random sampling, you take N sub J small units, you sample them from within the big unit, but you sample small units from every big unit that there is. So if you're doing, polling or whatever, trying to get nationally representative, do you approve of Biden, that sort of thing, you're going to take some number of people from every state. Now the way they usually do this, the N sub J's don't have to be the same for every big unit. So they'll usually make, you have 50, 51 states, and then we'll sample some number of people from each state in proportion to the state's population. So California gets like 40% or something of the observations in the data, and Wyoming gets like 1. So that's fine. But they're gonna put the poll to people in every state, even states that don't matter that much for national election purposes. So if you're gonna do your poll in all 50, 51 states, the big units are not random. And this comes into focus if you think about, what if I replicate a cluster random sampling study again? I'd have to get a different set of 50 or 100 schools randomly. There were going to be a different 50 or 100 schools from the 50 or 100 schools that the first guy got when they did the original study. And then, 10, 20, whatever people within each school, we'll sample those as well. If you repeat a stratified random sampling thing, where we're going to get polling, from a new set of people, we're going to get a new set of people from the existing 50 or 51 states. They're going to be different people than the people we polled last month, but they're going to be the same states, namely all of them. So with a stratified random sampling, the big units are not sampled. The big units are fixed. It's only the small units within the big units that are sampled. From a clustered random sampling, both the big units and the small units are ostensibly randomly sampled, in which case, from a frequentist perspective, the distribution of your estimator under clustered random sampling is going to be different and complicated and stuff that it needs to get worked out because you have two levels of randomization going on here. And so let's start with a model that has common coefficients, beta, across all the big units, and alpha, let's let that be a common intercept term, also sometimes referred to as a global parameter, even if we're not talking about like sampling across the whole globe. But global relative to the A sub j's, which is the deviation from the common intercept in the j'th group. Now, if we write the kind of the observation level of a generative model, we can write it like this. So this is actually the same on both sides of the equal side, but the interpretation of it differs fundamentally as to whether you take a Bayesian or a frequentist perspective on this. So from a Bayesian perspective, all this from alpha up through alpha j, or a sub j, is the conditional expectation function for mu, the expectation of y, given the x's of the small units, and the fact that the small units are within the j'th big unit. So this is conditional expectation of mu given x and the grouping structure. And then epsilon is what falls outside the conditional expectation. That is this random error noise for the ith person within the j'th group. And that's just basically a regular sort of error term from a Bayesian perspective. But the frequentists are going to have their own extraordinarily limited contrary perspective, which is the conditional expectation of mu given the x's of the small units, but irrespective of the grouping structure, it's just the alpha times the weighted sum of the x's. So conditional expectation of mu given x, but not j. And then consequently, okay, the Bayesian error is everything that's not part of its expectation. And then the frequentist error is the epsilon plus a sub j, the deviation in the intercept for all small units within the j'th big unit. And so from the frequentist perspective, the problem with these cluster random sampling things that needs to get solved is that the errors are not independent of each other. Every student within the j'th school is going to have a error, in general, a positively correlated with each other error, because every student within the j'th school has this shift by a sub j. Right? So within the same high school, the students tend to do like better or worse for reasons either pertaining to the, like, who are the teachers or the principals or whatever in the J school, or more likely, what is the socioeconomic situation for the neighborhood that the school is in. So for whatever reason, students within the same school tend to be better or worse. And so from a frequentist perspective, that's a problem, because the errors are not independent of each other across students. Within the school, you have very positively correlated errors. And so frequentists need to adjust their likelihood to reflect that. Otherwise, they would get vastly, overconfident confidence intervals and stuff like that if they pretended that all students within the same school are conditionally independent of each other. Now, from a Bayesian perspective, in a manner of speaking, it's similar because we're going to condition on the grouping structure. So, given that you go to this school, conditional on that, as opposed to irrespective of that, then, it's more plausible to assume that the students are independent of each other, but that leads to different estimates. And all this holds with GLMs, where it's eta rather than mu, and you're going to put an inverse link function to eta. Again, from a frequentist perspective, the only thing that goes into eta are the alphas and the betas and the x. Whereas from a Bayesian perspective, the a sub j also goes into the eta. And although that distinction often gets glossed over by applied frequentists who have no idea or don't want to think about any of this stuff and just do whatever the software allows, but what they do is contradicting the estimator that the software is implementing a lot. So questions about that? Okay. So we can do the same thing with slopes that vary by group. So we let alpha be the common intercept, let beta be the common coefficients, and let a sub j and b sub j be the deviation in the intercept, and b sub j be the deviation in the slope from the common intercept and common coefficients respectively. We can write the model like this. Well, again, this is the same equation, but different interpretation. From a Bayesian perspective, the conditional expectation, conditional on both the x's and the grouping structure, is going to include the a sub j and the b sub j times the x's business. From a frequentist perspective, the conditional expectation is irrespective of the structure, just includes the alphas and the betas. Consequently, what's left over from a Bayesian perspective is just like a regular error term. Whereas from a frequentist perspective, the error is going to include this and that. And these things are going to render the errors within a big unit not independent of each other, generally positively correlated with each other if we're talking about schools or whatever. And so they have to adjust their estimator to take that into account. Whereas with Bayesian thing, we really don't have to do much different. And that can be seen, we'll show it next. So just a little bit more about the frequentist thing. Frequentist perspective of these hierarchical, otherwise known as multi-level models, assume that the A sub j's and the B sub j's deviate from the common parameters according to a multivariate normal distribution whose variance and covariance of that normal distribution are common parameters to be estimated. And you might say, well, why are these frequentists making a multivariate normal assumption about these A's and the B's? And the frequentists, of all the ridiculous things frequentists say, in my opinion, this is the most ridiculous. Frequentists say, well, you can put a multivariate normal or whatever distribution you want, really, on the A's and the B's because the A's and B's are not parameters. So that's not contradicting, Fisher, etc.'s view that putting priors on parameters would destroy science as we know it. As long as we say A and B are not parameters, we're good. Now, in the frequentist somewhat defense, they do define parameters rather narrowly, as things that remain fixed in repeated sampling of observations from some population. And so if we're doing cluster random sampling, the schools and consequently the A and the B for that school is a random variable, because that school randomly got chosen and a whole bunch of other schools with different A's and B's and whatnot didn't. So what A's and B's you're dealing with is a random variable. It's a consequence of the realization of the first stage of cluster random sampling. But this seems like a rather arbitrary distinction that is intended to allow them to, or Fisher to continue to say Bayesian is evil because of the prior stuff, and saying, oh well, that doesn't apply to us because these are not actually parameters. But the way in which applied researchers do stuff when they do this in SAS or Stata or R or whatever, they treat the A's and the B's as like unknowns. So they're pretty much adopting a Bayesian perspective that these are parameters. But because they are not parameters from a frequentist perspective, technically speaking, they can't be estimated because they're not fixed in repeated sampling. If you do your cluster random sampling thing over and over again, you never get the same school twice as you repeat the study an infinite number of times. And so you have no ability to estimate the parameters of like the high school you graduated from, because that high school is going to appear in the data sets at most once. So you don't get a sampling distribution of that estimator, and so it can't be estimated. But it can be predicted, and this like totally flies over the head of all people who are using this, is the frequentist distinction between something that's estimated or something that's predicted. So if you had the alpha, if you had point estimates of the alpha and the beta, you could back out a prediction for the A's and the B's. But you can't estimate them. And as a result, when you go to do maximum likelihood, you have to integrate the A's and the B's out of the original likelihood function to get a different likelihood function that only depends on the alphas and the betas and the sigmas and whatever else is a common population parameter. And then once you have that new likelihood function, you can take the logarithm of it and maximize it, with the parameter values, etc. And that's really the reason why you see frequentists only and always assuming the A's and the B's have multivariate normal, because if that's true and also the outcome is normal, then the integral can be done analytically. So you can get a new likelihood function that doesn't have the A's and the B's in it. Maximize that. From a Bayesian perspective, this is all just comical. We're not going to distinguish between unknowns that can be estimated and unknowns that can be predicted. We're going to use the same probability framework for all that. We're not, or we could, but we're not going to integrate out the A's and the B's. We're going to condition on the structure and just draw from the posterior distribution of the A's and the B's and the alphas and the betas and everything else using Stan. Yes?
I still don't understand the difference between estimating and predicting A's and B's.
Yeah, well, no one else does either. Like, parameters can be estimated. Anything that's not a parameter can only be predicted from estimates of alpha and beta. So imagine you have estimates of alpha and beta and y. You could subtract the frequentist conditional expectation from y to get a prediction of the error. And then you can do some ANOVA business to separate out the predictions from the A's and the B's. But we're not going to do any of that. So just be aware that no one else really understands that fundamental distinction from a frequentist perspective either. They're just using frequentist software without really understanding how it differs from Bayesian software. So from a Bayesian perspective, this is what these multi-level models look like, and this is only slightly different from what we've done earlier today and in past weeks. So what we observe is the sum of eta and epsilon. Epsilons are normal and independent of each other, at least conditional on sigma epsilon. Might have an exponential prior. Again, I put the reciprocal there where I shouldn't have. As usual, we're going to construct this eta business, but that's going to include the a sub j's that deviate the intercept from the common intercept, and the b sub j's that deviate from the common coefficients in the j school or the j state. So also from a Bayesian perspective, it doesn't matter if we're doing cluster random sampling or stratified random sampling or none of those. We can just say our beliefs about the deviations in one group are normal or whatever. Normal prior on the alpha, normal prior on the beta. And from a Bayesian perspective, we're going to say, okay, usually, you don't have to do this, but usually bivariate normal prior on the a sub j's and the b sub j's. And we can make a bivariate normal prior with a marginal normal prior on the a sub j's and conditional normal prior on the b sub j's given the realization of the a sub j. We did that. We did bivariate normal construction. I can't remember when. At some point this semester. I don't remember what week it was, but I'm sure we had that somewhere. The way in which you draw from a bivariate normal is to draw from a univariate normal and then shift the mean, scale down the standard deviation to draw the other part of the normal. So this means bivariate normal prior on the a sub j's and the b sub j's. And then we're also going to have a prior on the standard deviation of the a's and the standard deviation of the b's, which can be exponential or whatever. And uniform, doesn't have to be uniform, could be uniform. Prior on rho, which governs the correlation between A and B in the same group, which is also an unknown that we want to estimate. So that's not so different from what we've been doing. What does it look like from a frequentist perspective? Okay, that's the same. From a frequentist perspective, the errors are normal, but their expectation depends on x. A sub j plus b sub j times x to the n. And consequently, these errors that you get out from this are correlated with the x's. And if you just did like regular OLS, that would be violating the assumption that the errors are independent. So to do multi-level frequentist modeling, you can't just do OLS. But that's when we get to the estimator. Here we're just talking about like what are the assumptions. So classic frequentist assumption, parameters are given. Now you might say, if they're given, why don't we have them? And that would be a reasonable question to ask. But if you were doing this on a computer, you would just fix sigma epsilon to be some value. And the same for all the other parameters. So then, okay, eta is alpha plus beta times x, but alpha and beta as well as x are given. You have this bivariate normal assumption on the a's and the b's, which looks identical to the prior bivariate normal that the Bayesians used on the A and B. Literally the same distribution. But from a Bayesian perspective, it's your beliefs about A's and B's. And from a frequentist perspective, it's not about beliefs. It's a consequence of you randomly sampling small units from the population of small units in cluster random sampling designs. And so this would be completely inappropriate if you had stratified random sampling design where the big units were not random variables, like California or whatever. Anyway, so we have that, and then given the parameters for the standard deviations and the variances. And so you might say, well, okay, I know frequentists do like simulations and stuff sometimes, but like if they're just going to assume all the parameters are given, what's the point? And that's another good question. Frequentists would answer, well, we fix the parameters to whatever, draw this, make this, push it through to A, and then we apply our estimator to A to see what its properties are across repetitions of all this. So we can say that the estimator is unbiased, which it wouldn't be in this case, or the estimator is consistent, or the estimator has like low variance or something like that across many repetitions of this process. But from a Bayesian perspective, there's kind of only one estimator, that's the posterior distribution, and we can like know the properties of that theoretically. But anyway, this is, Bayesian estimator is conditional on the data that you have. Frequentist probability pertains to the distribution of the estimator across all possible data sets that you could have. So anyway, got signed out. Questions about the generative processes? Let's go. Questions about? Yeah.
So the bivariate normal comes in play. So we each large group J, if there's a bivariate normal distribution of the A and B.
Yeah. And it's the same bivariate normal for all 50 states or all 50 schools. Like, it doesn't matter from a Bayesian perspective whether we're doing cluster or stratified. It doesn't even really matter if it's a sample from a Bayesian perspective. But from a frequentist perspective, it should very much matter, because frequentist multi-level models should only be used with cluster random sampling. But if you have cluster random sampling, then you really should be using a multi-level model. If you have stratified random sampling or anything else, you shouldn't be using this, because this assumption doesn't make sense if your big units are not random from a frequentist perspective. So this is the part of the vignette from the LME4 package, which is an extraordinarily popular R package for specifying and estimating multi-level models using point estimation. So it is basically frequentist, even though some of the people who contribute to LME4 are somewhat Bayesian. But anyway, the R syntax for this is to put things in little parentheses and have a vertical bar. Now that vertical bar doesn't mean given, and it doesn't mean or. It just means allow the intercept to be distributed normal with mean of 0. And you can have other structures as well, where you have like schools within school districts within states type business, so you can do the nesting. But most common are this one, which allows the intercept to be normal, and this one, which allows the intercept and the slope on X to be normal across the big units. But there's some other ones. Anyway, that's kind of the basics of the syntax, and both RCNARM and BRMS borrow those syntax constructions when specifying hierarchical models. So you saw in the Bayes rules reading that this can be done using the stand underscore LME4 or the stand underscore GLME4 or GLMER and LMER functions in RStanArm. They can also be done with BRMS. And one way in which like psychology, I think, differs from political science and economics, and a lot of times in psychology, particularly with these experiments or whatever, the big units are people. And the small units are like tests or tasks or like little activities that they have. And that's a bit different from political science and economics, where when we're talking big units, it's usually like a state within the United States or a country within the European Union or, you know, something like that. So what is a big and small unit? You know, it differs from field to field, perspective to perspective. The syntax is the same, and in psychology, I think a lot of it, like most of it, looks like this. You have some outcome, which is your score or whatever on the task, and that may vary depending on some X characteristics. But the people that you get, one, they're not really a random sample. They're just like whoever would take your $20. But whatever, they're big units. And so the sensitivity of whatever we're talking about, 2x, can vary from one person to the next. Maybe systematically, maybe it's just kind of arbitrary, you know, whatever. But it doesn't really make sense to say every single person has the same sensitivity to x, even for the same outcome. Just like people are heterogeneous. Heterogeneous. Can't say that word today. Heterogeneous. And then we also have some of this where we allow the intercept that goes into the question or that goes into the outcome to vary from one question to the next. And so most of the psychology experiments, they'll ask you like 20 questions, or they'll ask you to do 20 related things. And so you get this structure to the data where you have variation by person in terms of their personality or intelligence, whatever it is you're trying to measure. And then you have variation in terms of the questions or the games or the tasks that are being talked about. But the question of interest oftentimes is how to predict the outcome for a new big unit, a big unit that you haven't observed yet, big unit being person. As opposed to, it's not very often, but you could ask the question, well, how are we going to predict an existing person would answer a new question? Question being the small unit. You could do either one, the Bayesian framework accommodates it, but most often in psychology, they're like, okay, for this battery of tests or whatever that we've developed, how well does it predict a new person? Or how well will we predict a new person, what they would do if asked those questions? And so default priors in VRMS, not as good as the default priors in RStanArm in my opinion. But we can illustrate this with a tutorial that was actually written using RStanArm. So I think these data are not actually real. I think they're synthetic, but they were based on a real data set that they couldn't release for privacy or whatever that I don't know a whole lot about, and I don't know anything about psychology, but in my mind, what happened was they did an experiment where the psychologist poked people with a stick while asking them a bunch of questions. And so depending on how often or how hard they got poked with the stick or shocked with the electricity or whatever it was, people got more and more angry. And that affected their answers to whatever the questions were. So the valence of the response is the outcome, and that depends on how angry they were about being tormented. But both the intercept and the slope of that process vary from person to person. So some people are more chill, other people you scratch them with the stick one time they start having a fit, whatever. So anyway, if we look at the priors, we have a common coefficient on the treatment, basically. And then we have student T that's way too wide on the common intercept. And then we have what's called LKJ, but in this case it's just bivariate normal. So this is really just one correlation as opposed to a whole correlation matrix. We'll learn more about that next week. So really we just have one correlation to estimate between the A's and the B's. And then we have a standard deviation of the A's and a standard deviation of the B's. And those both have priors which are half student T by default, but again, I think that's all entirely too wide for most things in social science, even though BRMS is actually used in psychology a fair amount these days. So that's just repeating the Bayesian generative model. And so if we were to draw from this, we'd set up our, fix our hyperparameters or whatever, draw rho from a uniform, draw sigma A, draw sigma B from their exponentials, construct this business, which governs how the conditional distribution of B given A is affected by the realizations of sigma A and sigma B and whatnot. Draw the common slope, the common intercept, the common standard deviation of the errors. And then in order to draw outcomes when we have this hierarchical structure to the data, we're going to have to do a group by statement and group by whatever the big units are. Schools, states, people, doesn't really matter. We're going to do these steps for each big group. So summarize, draw the A's for the jth person, normal. Draw the B's from the for the jth person, normal but conditional on the A's. So it's bivariate normal marginally between those two things. Use the A's and the B's, those go into the etas. So construct the predictions for each person. So yeah, each person, there was like 20 people and they all had 15 questions that were asked of them while they were being hit with a stick. So for each person, they're going to have 15 eta values over time. And then there's a epsilon for each person and time period. Those conditional on the A's and B's, the errors are independent. And then y is just the sum of eta plus epsilon, like we have at the top there. So it's basically saying when you have this hierarchical structure, each big unit is like a mini population. And then you have to do the A's and the B's and the construction within each big unit, and then ungroup it at the end. So now you have this like two-level hierarchical structure. And I mentioned neural networks a little bit in passing. They've certainly gotten super popular, but they're not that great, particularly if you get point estimates of them. But kind of the essence of them, it just sort of looks like a generative model, except not taking the parameters from distributions. But the idea of like, you have a top layer or a bottom top, usually the way the neural network people, something's going on there, and then it gets fed into what they call an activation function, which to us just looks like an inverse link function. And then it goes to level 2, and then more unknowns and stuff, and then it all gets mixed together, and then it goes into the activation or inverse link function for level 3. And then they have like 5 levels or something like that, and then eventually it hits the data. So it looks a lot like what we've been doing, especially today with the splines and stuff like that for estimating these like smooth but not linear functions. It's just they don't have priors about the unknowns. End up getting point estimates, end up overfitting. It's not as great as it sounds. So anyway, to estimate this in VRM, we put in the syntax to say that can specify priors over the common parameters. The other things, the default, I guess, is okay. It runs, you get estimates, and that is going to include what BRMS calls population level effects. So the alpha and the beta that pertain to everybody, as well as group level effects. So in this case, there's 20 people in the study, and this is estimating the standard deviation of the A's, the standard deviation of the B's, and the correlation between the A's and the B's. Now again, we get 4,000 draws on all of this. This is just the average and the median and those things. But it doesn't even show the A's and the B's, because for psychology, that's usually like not super important. And then we also have, posterior draws of the sigmas that pertains to the epsilon. And it had an average of like 9.5 or whatever. Decent to good effective sample size on everything, so that all goes well. And then once we've got our thing in our state arm or BRMS, we can apply every function that works with objects that are produced by the respective package, including the proto-smooth important sampling leave one out estimator of the expected log predicted density. If we wanted to compare this model to some other model applied to the same outcome, we get this. Diagnostic values totally in the okay or good range for all 272 observations. And okay, we've got this, we can compare it to another model. You see this, which we haven't really talked about that much yet, effective number of parameters 26. And that is in contrast to the nominal number of unknowns, which is 46, which is like the number of columns of posterior draws that we have 4,000 of. So this effective number of parameters, you can think of it as this model has about the same variance as a model that had 26 parameters but no priors. So the fact that we have this hierarchical prior structure to it means that we have a posterior distribution of 46 unknowns, but because we have prior information about how those unknowns relate to each other with the bivariate normal on the A's and the B's, it's sort of the equivalent of 26 parameters with no prior information. And this often happens. Bayesian hierarchical models, that the effective number of parameters is much less than the nominal number of parameters, and that is due to the partial pooling or shrinkage that was talked about in the Bayes rules reading for today. You can also do prior predicted checks that respect the grouping structure. So here we have 20 people in the so-called experiment, and the horizontal axis, like in my mind, it's the number of times they got hit with the stick. It might be the time or something else, but it's related to the treatment, whatever that was. And you look at this and you say, okay, model seems to be fitting okay, but particularly in the social sciences, maybe particularly psychology, when you look at these things, the model makes way more sense than the data does, because the data come from people, and people don't really make sense. So like person number 9, like they got really angry when they got hit with the stick the 41st time, and then they got like really calm, and then they got really angry again, like the 42nd and the 43rd time. And that like doesn't correspond to any theoretical model of psychology, including the theoretical models in psychology that are put forward by non-psychologists like myself, who can't even describe what this study actually was about correctly. But I know person number 9 does not make sense under anybody's theory. But the model kind of smoothed over the weirdness of person number 9. But actually all these people have some weirdness to them, except person number 13. And it's weird that person number 13 would not be weird, because like 13 is a weird number, but like, what's going on? Anyway. And so by doing these multi-level models, the model gets less preoccupied with any one person or one big unit. And that can be especially effective in situations where who the big units are kind of arbitrary, which is like always the case in psychology. You're not really interested in the psychology of any one particular person, rather people in general. And so when we do posterior prediction, yes, we can do posterior prediction of previous people. We can use that to do posterior predictive checks and whatnot. But we can also make posterior predictions for a new person. So if we just construct a data set that's like the first person, but we change their ID to be something other than 1, So now it's a new person who has the same X as person 1. We get posterior predictions of that new person. And you might say, well, if we haven't observed that person yet, how can we predict them? Well, we just apply the same generative process, but now use posterior draws rather than prior draws. So we draw person number 0's A's and B's from bivariate normal, given posterior draws of all this, form the eta, draw an epsilon, and then add those together to form our predictions for the outcome for person 0, who we haven't observed in the 20 people that we did observe. Okay, so out of time for today. I will post the last homework tonight. It'll be due next week. And we will have recitation and office hours on Tuesday as usual. And then next week is the last class, and we'll get into more detail about the multi-level models and hierarchical models type stuff. So see you then.
Is the final at this point?